for AWS to give me a chance to be here today and to talk a little bit, to introduce a little bit our new technology. My name is Phạm Văn Hòa. I'm a welding engineer. I'm working for Master in Vietnam now. And this is Master. We are the biggest industrial gas company in Vietnam. So we support the shooting gas for whole Vietnam from the north to the south. So please, yeah. Yeah, we have to need to wait a little bit for support too. Thank you so much. For my topic today is introduce about our new technology about high cut with the growth opportunity for use hydrogen like an alternative gas for cutting. You know, in the oil field cutting, we usually use acetylene LPGs, but in Messer now, I don't think that's new, but we apply application the gas. The alternative gas is the hydrogen for the fuel gas. It's not working. Okay, thank you. Sorry. Of course, it has to be become with the goal and the opportunity. The hydrogen as a sustainable fuel gas for alternative the how to say classic gas. For God and opportunity, of course, to increase the environment awareness for all of us, for the world, and for the employee, the worker. Also, they reduce the carbon footprint. Another thing is energy saving with hydrogen and improve health and safety for working environment. That's our purpose for alternative gas with hydrogen. Of course, you are here or is expert in welding and cutting. You know, for the OCView technology in fabrication has a lot of application like cutting, straightening, or heating, or maybe welding, soldering. So, about the motivation to use hydrogen, ESG is driving force. Of course, everybody, every country in the world talking about ESG thing. Tack on hydrogen carbon fuel gas also avoid instead of using the LPG or acetylenes. Work safety is also an aspect gaining more important in the world. Also fuel technology with the process like cutting, heating, straightening, and soldering mainly operated with the fuel gas, propane, acetylenes, natural gas. In principle, all of that process we could can be replaced by hydrogen. That's what the master purpose here. We were talking a little bit about the advantage of hydrogen in also fuel technology when you use hydrogen. We do some, comparison about the CO2 emission during the flame cutting, and here is the result. With the hydrogen, you could see that has no carbon atom in the molecules. Of course, when we compare, you could see in the frame over there, approximate 6 times lower CO2 emission if you compare to acetylenes, and almost 10 times lower CO2 emission when we compare with propane when we're cutting. So that is very important for, CO2 footprint reduction. For nitrogen emission in comparison, up to 75% of lower nitrogen oxidized emission compared to acetylene with the frame over there. You can see. So you're gonna be, concerned how can we calculate and have a result like that. This is our experiment, and we cooperate with the Hanover University in Germany, and how we have a box here, and we have extracted a device here, and we got all the dust, all the fine dust, and all the film, and we calculate it. And this is the result of the dust. You can see with CO2 we has much more lesser than compared with acetylene and propane. And this is very good for work environment for worker. About the sound, the light, and the performance of the production, we calculate and we measure when we're cutting or heating with the hydrogen, the sound level is lower 3 to 10 decibel depending on the application. It depends on cutting or welding or how to say heating. We estimated the spectral color in the flame light, so there's no harmful light. It affects to the eyes of the worker, so that's a good sign with cutting with hydrogen. And with our equipment, we got high cutting speed and very short searing time compared to LPG and acetylene. Of course, with hydrogen in compressed gas with high volume, now in hydrogen in Vietnam we have 200 bar in the cylinder of 50 liter. I know everybody here will concern a little bit about the safety when you change from the LPG and hydrogen, and this is characteristics of hydrogen and acetylene and propane. Before this presentation, I got the answer, the question from Dr. Cho here about the safety. For master in all the world, we really concerned about the safety, and safety always the first thing we think about. And this one still on the research for the safety of hydrogen. But we have some customer in Europe now using hydrogen now. Of course, in Vietnam, not yet. We did some demonstration in Vietnam, in vast shipyard and some shipyard in the south, but not yet in the customer. They're using now because of hydrogen price and also the equipment price if you compare with the other method. But one of the most important thing is with hydrogen in Europe now they use up to 300 bar in the gas cylinder, and we don't need the solvent required if we compare with acetylene. We need acetylene to dissolve. About the equipment for this application, we also have a machine cutting torch. We also have a hand cutting torch. We have a cutting insert, and we also have a special nozzle for hydrogen. We also have a very special torch like that for heating. We also have the other application like welding, heating, and flame shortening torch. In Vietnam now we have a lot of kind of thing to supply hydrogen to the customer. We have cylinder, we have a bundle with almost like a 16 cylinder like that. And we also supply to customer with tip chiller like this one. So in Vietnam right now we have a total from the north to the south of hydrogen plant, so easy for us to supply the customer in Vietnam. Of course, that's all. Thank you so much. Thank you. Yes, please. Yeah, thank you. Yes, sir.
As you know, hydrogen in reaction with oxygen will extract water. Water is vaporized. That is why harmful effect on the quality of cut, especially with welding. How we can resolve this problem? And the second one, explosion, very dangerous when we transporting or operating.
Yep.
Two questions.
Okay, I just heard clearly from the second question is the explorant with oxygen, right? Yeah, yeah. That is the concern of from us and also from the other people when they use. Right now, we really don't have something like a safety 100% for customer to use us. So that's why we produce some safety device like flat back arrestor for hydrogen to keep the safety. And about the leakage and anything else, I think I will get contact from you and the question from you and talk. I will connect you with our expert in Germany and also in Asia, so to make the question more clear. And the first question, sorry, I don't hear so clearly. Sorry, sir.
How about water?
Other water.
Vapor of water extract from the reaction between hydrogen and oxygen.
Okay, you mean in the process there will be the water in the process, right? Okay, that's a big question for me. I will get your contact and answer you later. Okay? Thank you so much. I never think about that before. Thank you. Thank you so much.
Vâng, và tiếp theo sau đây xin được trân trọng kính mời ông Trần Văn Châu đến từ Học viện Kỹ thuật Quân sự với chủ đề Laser Direct Energy Dispositions of Tungsten and its Alloys. Lắng động năng lượng trực tiếp bằng laser cho Wolfram và hợp kim. Xin được trân trọng kính mời ạ.
All right, so good afternoon, everyone. Thank you for coming today in the 19th Asian Welding Technology and Application Forum. So my name is Cho, and I come from Advanced Technology Center in Lequidon Technical University. So the topic for my presentation today is the laser-directed energy deposition of tungsten and its alloy. So here is the agenda of my presentation. It includes the introduction of additive manufacturing, aka 3D printing, and more detail about the laser-directed energy deposition. After that, we will briefly review the tungsten and its alloy characteristics. And then we want to show some pilot experiment as well as the challenges of the LED for such material. And finally, is discussing some results and conclusions for the last. So let's start with the introduction of the AM or 3D printing. So this figure demonstrates the comparison between the subtractive or conventional traditional manufacturing and additive manufacturing approach. As we already know, that is the subtractive manufacturing, we can say it's a top-down approach. So this traditional method like CNC milling or turning, you start with a solid block, and then you will use the cutting tools to remove volumes. While additive manufacturing is the kind of bottom-up approach. So this is 3D printing. The part is built up layer by layer from, of course, we have some digital files. So the advantage is something you can see clearly is the efficiency. Like the only material used is what ends up in the final product here. And in theory, there is very little waste. And here is the evolution of additive manufacturing. It has a long history from prototyping to industrial production. And yeah, for the AM classification, is we can classify additive manufacturing technologies into mainly 7 methods, such as sheath lamination, powder bed fusion, directed energy deposition, biojetting, and so on. And in 7 methods here is only, there are 4 with a rectangular mark can be used for printing metals. And another classification of the metal processes can be based on whether the thermal energy is used to melt or sinter the material, and others involve only material deformation, which can be further divided into more detailed branches as shown in the image here. And for the 4 AM methods I mentioned before, we can see that is the directed energy deposition is absolutely more suitable for printing the metal parts. And it actually offers high density parts, high deposition rate, as well as ready for use with multiple materials. Oh, all right, so let me briefly introduce about the metal additive manufacturing research at our university here. So we have invested 3 types of metal AM system, including the selective laser melting, laser directed energy deposition, and wire arc AM. So the 2 left of them are commercial system, but the right one is the self-developed. So that means we can access the machine and change any part, any kind of thing in that machine. So we mainly use the right one for our research. And in this topic here, we also utilize that kind of system to do the experiments. All right, so let's talk a little bit more specific about this kind of system. So it is 3D DOF, that means we have XYZ axis, and working space is pretty small because that is for experiment, it's 160, 160, 200. And about the material, we can use any kind of powder in theory. Of course, if we can seal the chamber well, and we also use a fiber laser with the power source is 500 watts. And for the protection gases, we can utilize argon or nitrogens. All right, so let's say how LED work. Like I have a video here, so hopefully that it can run well. Okay, we have a focused laser beam hits a small area of the substrate, and the metal feedstock, usually the powder or wire, is delivered into the molten pool. And then the material melts and solidifies quickly, so we can utilize the robot arm or CNC system to move the deposition head. So because it is very high energy short and highly focused laser beam, the process can melt almost any kind of metal and alloys. So making it very promising for difficult to machine material. So other than that, the process have advantages like within the system, we succeeded printing stainless steel, titanium, inconel, and so on. So one question that immediately pop up is, what about tungsten? Like, tungsten is well known for it is difficult to machine characteristic, like it's very high melting point, high hardness, and very good wear resistance. So that means it's very difficult to cut it. And then is so due to this kind of extremely high melting point, hardness, and density, excellent wear and heat resistance, tungsten actually used for cutting and machining tool, welding electrodes. We only know for the thick electrode, and aerospace, defense, and heat shield, as well in electronic and electrical application, especially like in fusion reactor, they can use for the radiation shielding. So it sounds promising in theory, but however, to do printers, tungsten and its metal alloy is not easy at all. Like first is cracking and brittle behavior. So we know that tungsten is high ductile to brittle transition temperature. So it is the rapid heating and cooling cycle from the laser processing that will create massive thermal stresses, leading to the solidification, cracking, and intergranular fractures. So the next challenge is about the densification issue. So to achieve full density is very difficult because the high melting point and low laser absorption. So let's talk about the laser absorption. Like for the tungsten, the laser absorption, for example, with the fiber laser, actually pretty low, like lower than 30%. So it's require very high energy density, which can cause the key holding or evaporation of the material. So third is we want to face some like defect or incomplete melting. So like a fusion in the LDED of tungsten is mainly caused by the insufficient melting or poor wetting between the deposited layer. And last but not least, like tungsten is very high oxygen affinity. So that means it's very, very easy to oxidize in kind of non-inert environment. So when the tungsten reacts easily with the oxygen at high temperature, so it can making oxide formation. So that kind of factor weakens the grain boundaries and promotes cracking. So we try to conduct some pilot printing and tests on tungsten using our system, as we saw before. So before doing the experiment, we determined that is some kind of key parameter we need to control, like the laser power, scanning velocity, as well as the laser beam diameter or power gas flow rate. But in this very pilot experiment, we just focus on the laser power and the scanning velocity here. All right, so let's talk about the material. So we try to use material like a pure tungsten powder, within the particle size is around 50 to 75 micrometer, and we use a substrate is like stainless steel SS304. Yeah, so this is some very first results, like we vary the laser power and we cut the sample to see what is the inside the structure of the printed layer, and we can see that it's like the bit dimension increase when the laser power increase, of course. But when the scanning speed smaller, the higher volume density, like the bits become larger and unstable. And we also make a thin layer, very thin layer, but only single layer and 2 layers of the material on the same substrate, and we can see that is somehow the tungsten particle can be melted and partially melted into the substrate. Right, but something we can notice here, like for only single layer, we can see that the surface is pretty smooth, but upper to the second layer is surface like increase unstable, and this is maybe caused by the insufficient energy inputs, and whereby the tungsten particle are unstable to fully melt. Yeah, and it is kind of difficult to achieve the good wetting and spreading material. And we also use the SEM to see how really the microstructure inside the deposited layer. And we can see, like in the image here, we have the substrate zone, the mixing zone, and the partially melted tungsten particle. All right. All right, so to this image is shows the EDS spectrum and elements or mapping in the mixing zones. So between the substrate and the powder after scanning, so we can clearly see the elements like iron, tungsten, chromium, and nickel. And there are some main elements inside the composite material here. So although some studies have identified such a feature like that black particle there is unmelted tungsten particle, but depends on our observation that actually some more rounded morphology suggests that this particle was partially melted rather than retaining their original shapes. And we also do some kind of light, EDS light scanning through a partially melted tungsten particle. So of course we can see like in the center of the particle, there are almost no ions, nickel, and chromium. It is only tungsten. But if we see something like, okay, here in this area, like a slope, so that means is in the boundary of the tungsten particle, it's actually partially melted and mixing with the base elements. And other than that, we also produce some like micro hardness measurement. And we also measure as a base material, the mixing area, and inside the tungsten particle as well. So we can see here, of course, the base temperature with very low hardness. Higher than that actually is the tungsten particle. So the mixing zone has the highest hardness here. It actually is because of the intermetallic structure. All right. And for deeper understand about the crystallization of the sample, we produce HRD's analysis here. And on the right side is the HRD's analysis for only tungsten powder, and on the right side is for the LDED sample. So on the LDED sample, some kind of tungsten, and metallic structure appear in the peak of the HRD here. All right, so to investigate the grain morphology and the crystallographic orientation, we produce EBSD characterization. And we can see also like phase changes due to the LDED process. All right, so it's some very fancy image of the band contrast and IPF of the LDE sample. All right, so for conclusion, is we somehow successfully deposited the pure tungsten on stainless steel using the LDED process, and we can measure some kind of parameter and analyze the elemental and mixing zone and so on. Also, for the future research is we suggest like develop crack-free processing strategies and advanced alloy design. Like now we just deposit the tungsten powder on the stainless steel, but somehow we can mixing other kind of powder to achieve very advanced features. That is our plans. Right. So last but not least is we thank the Advanced Technology Center and as well as the Zoning and Welding Research Institute. It's from Hanoi University of Science and Technology and University of Osaka for their support. Right. Thank you. Thank you very much. So if you have any questions, so please ask.
Yes, Mr. Joe, thank you very much for your interesting presentation. But I have one question only. Since you are feeding something like powder to the area of melting, can you present me the size and morphology of powder? Because depend of the size and morphology, the feeding rate is keeping stable.
Right, so thank you very much for the question. So here is, we use tungsten powder, and you can see, sorry. Can you show me this image again? Yes, so here we use pure tungsten powder, and this chart is the particle size presentation. Like the powder is mainly around 50 to 75 micrometer in diameter. Yeah. Yes, sir. Okay, Henrik.
Okay, very good presentation. I have three suggestions. One, maybe the powder itself affected the crack sensitivity heavily, according to my experience. Yes, actually, if you 3D print pure tungsten, the crack easily accurate, you know. But I think the powder itself, made from different technology, will affect this. This first suggestion. The second one, you already mentioned in your PPT, alloy, tungsten alloy will reduce the crack. Okay. The third one, suggestion, is that normally we use a commercial 3D print machine, and the temperature field is too great, and the temperature decreased so quickly from the welding pool. If we use modified the beam, maybe the result will be better. Yes.
All right. So thank you so much for the suggestion. Like for the third suggestion is I need to, yeah, you are absolutely right. In here we actually use a self-developed LDD system. So that means we build the system from scratch. Like we build a laser and optical system as well as the XYZ movements. So yeah, like for changing the, if I understand the suggestion correctly, like somehow I can change the beam spot, right? Yeah, right. So in here is that we can easily change the beam spot by changing the working distance. That is the easiest one. As well as we can change the optical system inside our machine. Yeah. So, any questions so far?
Thank you for your presentations. Và ngay bây giờ xin được trân trọng kính mời ông Terumi Nakamura đến từ Hội Kỹ thuật Hàn Nhật Bản sẽ cùng đến với chủ đề Expanding Additive Manufacturing Technology Using the Data Platform System, mở rộng công nghệ in 3D sử dụng nền tảng dữ liệu. Xin được trân trọng kính mời.
Thank you. My name is Teru Nakamura and Japan Welding Engineering Society. I introduce expanding additive manufacturing technology using the database. Additive manufacturing is metal active manufacturing technology is adapted as the production method in manufacturing technology. However, additive manufacturing technology have several challenges to use. First is variable properties. Properties of built part by AM such as density and strength, vary by process parameters. Next is complex parameters. Metal AM has many manufacturing parameters and many parameters and manufacturing parameters and process parameters. This makes it difficult to set a suitable condition. Last is high entry barriers. Primarity tests are required to determine the property and parameters. This leads to cost rise and development time become long. These factors give a great burden for SMEs and startups. So, AM technology is not used widely in manufacturing. So, the Japan Welding Society, the aim of the Japan Welding Society is expand AM technology. We set the two initiatives. First is development of database to support AM design. Next is AM education system to expand AM design engineer. This is the manufacturing process for the conventional manufacturing process and AM manufacturing processes. Conventional manufacturing process, design engineer create the component design and write the engineering drawings. Next, production engineer makes the recipe for product manufacturing. Production engineer creates the shape drawing and selecting machining method. For example, shaping, casting, forging, and in addition, and additive manufacturing. This is AM manufacturing processes. AM design engineer, there is AM design engineer must part design and product AM processes and design production design. Part design, the AM design engineer draw the engineering drawing and design new shape and suitable design. AM process, the AM design engineer select the AM processes, powder bed fusion or DED and other processes. And AM design engineer select the AM condition, parameter setting or optimization of shape and property. So in this show, the AM design engineer required wide range skill and knowledge. So, to increase AM design engineers who understand the characteristic of AM and perform suitable AM design, we thought AM education and other process is important. So, AM education, knowledge of the design for AM and topology optimization and DFAM, design for additive manufacturing is very important. First, we showed the AM education system in develop the JWES. This is the JWES AM Engineer Certification System, JAMECS. JAMECS is a certification program to train engineers who can understand AM and efficiently utilize AM. This education system divided 3 parts, level 1, level 2, level 3. And level 1 is basic. Level 2 and level 3 is specialisted for the specialist. And level 1 started 2025, and level 2 will start 2027, level 3 will start to 2028. So the level 1 training course is holds 3 days. The textbooks and PowerPoint file for the AIM Engineer Level 1 is made, and written examination is carried out. For the Level 2 and Level 3, oral examination and written examination will be carried out. EWF is the made the AM certification system. JWES is implementing the body of IAMQS. IAMQS is International Additive Manufacturing Qualification System. So the JAMES is designed so that candidates who pass the level 1 are given the CU00. CU00 is competence unit record, gives the CU00 record of achievement ROA. For example, the coordinator, the training lecture training time is 185 hours. So after the examination, the coordinator diploma is obtained, and JAMES system is designed so that the characteristic, so that the candidate obtains the CU00 system. This is the lecture time and part of competence unit. This is the coordinator. The 185 hour is necessary. The CU00 is basic competence unit is like this. So next is, so the aim design is carried out, the conceptual design is carried out, the appropriate shape of the parts is designed, and the solution is selection of the material is selected. After the conceptual design, feasibility of manufacturing is carried out. We investigate whether we can build parts by manufacturing and equipment. So the basic test examination is carried out. The basic specimen like this is made by the active manufacturing. But there is some challenges specific to property of building parts. So variable properties of building parts.